Okay, I will get started. It is a great pleasure to welcome Professor Yamil Colón from the University of Notre Dame to our IIDAI seminar series. Professor Colón got his undergrad degree from University of Notre Dame in Chemie, working with Paul Bohm and Yin.
And John Brannigan.
Oh, John Brannigan. And then went to Northwestern for a PhD with Randy Snur, where he worked on computational discovery of inorganic frameworks. And then a postdoc with Juan de Pablo at Chicago, where he worked on a variety of things, including self-assembly of inorganic frameworks. Then started his career at Notre Dame in 2018, 2019. Mm-hmm. And he's won a number of awards, including an NSF Career and ACS PRF Doctoral New Investigator Award. His work is right at the interface of machine learning, chemie, StatMech, absorption, lots of cool stuff. We're very happy to have him here today. So take it away.
All right. Thank you, Nick, and thank you for the invitation. Yeah, really happy to be here. It's been a minute since I visited, even though it's just a 3-hour drive. So I'm happy to be back. And yeah, thank you for so far. It's been a great visit. So, okay. So I want to talk to you about some of the workflows that we've developed in the group to do molecular and materials characterization from a computational standpoint. First, of course, I want to acknowledge those who actually do the work. So Krish, who just defended his PhD, Denise, she's now a research professor in Portugal. Osado also recently defended, and Gregory Cooper, who was an undergrad working with us in the group. And then I have multiple collaborators at Notre Dame, Professor Luo, Professor Dowling, McGinn. And then also want to acknowledge Professor Gomez Calderon at Colorado School of Mines and our computational and funded resources. So I want to give you a bit of a perspective of how do we think about materials and sort of technology moving forward? So we think a lot about the fourth industrial revolution. And so let me walk you through this. So first one in the 1780s was steam and water coming to the picture. Then 1870s, electricity. In 1969, 70s, IT. And so now, given artificial intelligence and the increasing interconnection between technologies and in many cases our own bodies, many people feel that we are currently living in or about to embark this fourth industrial revolution. Okay, so let's put that futuristic hat on for a second. And so I think some of the things that we think about as chemical engineers, the future of energy. Then we think about catalysis, we think about solar energy, things like that, healthcare, infrastructure, the environment. So you start going down those paths, and it doesn't take very long for one to realize that that future that we have or that we think about is really dependent on advanced materials. Right? So advanced materials are the ones who are going to enable that future, right? So future of energy, yeah, those materials that give us better catalysis or allow us to have more efficient solar cells. Health and healthcare, advanced sensors that will help us diagnose disease. We have better materials for drug delivery, targeted delivery, infrastructure, smart materials that self-heal or that tell us when things need to be replaced in a timely fashion. The environment, things like carbon capture, better materials for separations of rare earth elements, so forth and so on. So all of those technologies, the foundation is advanced materials, which then begs the question, well, where are those materials, right? Maybe they already exist and we just need to kind of put them in a new context. Or maybe we need to discover them altogether, right? Maybe we need to think about new ways of combining materials or use new techniques like machine learning to help us design and discover new materials. So that's kind of the way that we think about things in my group. And so here are some of the things that we think about. So we think about porous materials for the water energy nexus. So the water energy nexus refers to this intricate relationship between how much water is necessary to produce energy, how much energy is necessary to produce water. In our case, with porous materials, we think about water vapor adsorption. So things like atmospheric water harvesting, for instance. Like 10% of the world's freshwater resources are actually in the air. So you can think about developing new materials that are capable of capturing water, being able to deliver it, and then the energy required to do so. Okay, you also think about carbon capture in the presence of water. Talk to anybody who deals in that space, right? Anything that likes CO2 don't like water anymore. Right, so then there are opportunities there to have synergistic effects, or right, think about new strategies of how do you control interfacial interactions to favor one thing over another in the context of those separations. So we spent a lot of time thinking about that. And we're also thinking about new classes of materials. I call these soft porous coordination polymers. So these are these porous cages. So this is called a metal organic polyhedron, or a MOP, which has these open metal sites here, which if you connect them all and you're able to fulfill all the coordination sites, and you do so with these types of linkers, you can get sort of this FCC, an FCU topology like crystal. Now what happens? These linkers, if you make them flexible, so here's this CH2 here that almost works like a hinge. What ends up happening in this type of crystal is that this big pore that you see here is actually unstable. So what happens is the structure collapses. But now you have this pore that's given by this small cage, that's permanently porous, that's not going to collapse. So now you have something that's permanently porous, but has the ability of changing its porosity depending on how much gas is inside, which gas is inside. So now you can think about the different processes in terms of delivery, gas absorption, unique absorption, desorption kinetics. You also have amorphous versions of these materials, and also thinking about, well, what does the pore structure look like? How does absorption affect the various configurations and so on? So we're working on that space. In my line of work, we do a lot of hypothetical material screening and generation. And so the question we always get asked is, you generate a new material, how do you know that you can make it, right? One of the ways that we're trying to address that question is actually modeling their self-assembly. Okay, so we've looked, right, if you think about the self-assembly process of something like these crystalline type materials in metal organic frameworks, you have the formation of secondary building units, their aggregation into some sort of amorphous cluster, a transition to a crystalline state, and then you have oriented attachment type events to then wrap up then the reaction, then you have your crystals or your decided morphology. So computationally is extremely challenging. You have a very large time and length scales that you need to be able to model and to link together. And so we're looking at machine learning potentials to help us model these processes with enhanced sampling techniques to understand the free elements. Now, we want to understand, of course, how you make these materials, like what are the potential synthetic conditions that will give rise to any given material, but also understand how do you control their morphologies, right? One of the reasons we want to understand those morphologies is to actually use some of these materials in quantum technology, photonic quantum technologies in particular. One of the reasons we want to control morphologies, we need large single crystals. So you speak to anybody in the MOF community, getting large MOFs, single crystals is extremely difficult. But we need that in order to actually test experimentally some of the problems. Computationally, what we have done is now developed a multi-scale method that allows us to actually evaluate these materials and their ability to produce entangled photons. So now we can look at structure property relationships that link the properties of the entangled photons, things like correlation times, effective brightness, back to the actual chemical and material properties of that crystal that you have. Okay. We're also looking at other systems like ionic liquid. So these are salts, liquid salts. And because they're very charged fluids, people have been looking at, well, how do they respond to electric fields, and can we use them for separations and other types of applications. And so we're looking at sort of basic thermodynamics of, well, how do these fluids then respond in the presence of electric fields, and what are the thermodynamics and new really physical properties that arise in these systems that, you know, they're being looked at in solid state materials, but in liquids is still very much unexplored. And so within sort of all these projects, right, you have potential materials, right? You think about nodes, linkers, think about temperature, pressure, composition, right? Just doing the molecular modeling itself, right? Even just you computation, it's unwieldy, right? It's way too difficult for you to run all these simulations. You need incredible amounts of compute time, not available usually in that. Right, so in that case, then we bring in machine learning to help us decide, well, what are then those conditions that I need to test for me to understand these landscapes? Okay, so we're gonna look at that from a thermodynamics standpoint, so like my temperature, pressure compositions that I need to be thinking about. But also we can think about also navigating the molecular spaces that way. So I'll talk a little bit about sort of not necessarily new descriptors, but in this context, new descriptors that we can combine with these machine learning algorithms to help us explore and navigate these molecular spaces. All right, so I want to start with our story about porous materials, in this case, metal organic frameworks. So these are crystalline nanoporous materials that self-assemble from inorganic nodes and linkers. So inorganic nodes and organic linkers. So you have a great variety of building blocks, right? That's intentionally clean, right? So you have potentially sort of all the chemical palette of inorganic and all the ones from organic chemistry, right? All these combining to form these materials. So the potential material landscape is quite large. In addition to that, you can then introduce functionalization into the linkers or the nodes, you know, before you make the material or after you make the material, right? So the opportunities to engineer these materials for particular applications, given that design flexibility, is something that's extremely attractive. So they've been looked at for many applications, right? You have things like drug delivery. I talked a little bit about moisture harvesting, which is also relevant not just for atmospheric water harvesting, but also refrigeration cycles, for instance. You have detection, you have CO2 capture, various separation applications, diagnostics and sensing applications for disease, so forth and so on. Okay, so I want to give you a bit of a sense of sort of the diversity of the space that we're dealing with. So, for instance, you have something like H+1, which is this copper zinc paddle wheel, which is connected by this benzene tricarboxylate linker. And you form this three-dimensional structure. And so immediately we see, right, you have this large pore here, which mostly has this benzene, so this aromatic group here exposed to the pore, but then you have this smaller pore here, which mostly has then the metals exposed to it. Okay, so now you have different chemical environments being available to you within the same structure. So you can now start thinking a little bit creatively about how to use that to your advantage for various applications for energy storage, catalysis, and so on. You have something like CIF71, so you have these very tight windows leading into a large pore, so separation applications become attractive. Then you have things like MOF74, so you have this one-dimensional channels with these metal sites exposed, and so they've been looked at also for catalysis and separations applications. Right, so you have a very wide range of topologies and chemistries that are available to you, okay? And so the way that we've been thinking about this is, okay, well, there's so many materials out there. What the community has now done is develop a suite of techniques that allow us to quickly either generate and characterize these materials in an efficient way. So we have databases of materials, okay, and then you can do the physical characterization, look at what is the surface area, the void fractions, like pore size distributions, and so on, and also characterize things like absorption. So once you start dealing with these high frequency, large scale screening techniques, then you get into presumably a lot of data. Okay, so now when you get a lot of data, machine learning starts to come into the picture. Yeah. So what I have here is sort of the workflows associated with machine learning. In this case, I have it here for MOFs, but this is not unique to MOFs. I would argue that anywhere in the molecular sciences in general, this is your workflow. You have a database of chemistries or materials, okay? You need some way to characterize them and get your data, okay, which then you're going to use to train some algorithm. And then that database, you also need some way of turning it into something that a machine learning algorithm can understand. Okay, so you need a way to develop your descriptors of your database. Okay, you need ways to get your data, and then in many cases, you also need ways to get at the database to begin with. Right, you can think about experimental databases of materials. Right, so we saw the meta announcement. I think it was yesterday. Right, about this like 6 billion, something like that.
100 million chemistries.
100 million chemistries. Thank you, Nick, for the assist. Right. And so we have, for our case, right, we look a lot at the chemical structural database for materials. Then you can think about sort of computational approaches to generate the materials and the chemistries also associated with these databases. Okay, so we have, in my group, we have sort of research projects along each one of these various parts of this machine learning workflow. Okay, now, when we think about sort of these machine learning workflows, I would argue that the data is actually the most important. And what do I mean by that? Well, everybody wants to think about, oh, when are we going to get our ChatGPT for materials, so ChatGPT for chemistry, right? I think that's a very laudable goal, but we're still very, very far from reaching it, right? And this is one, okay? In order to train a lot of these algorithms, we need a lot of data. Now that presents an existential crisis really for chemistry and materials. If I need a lot of data, right? That means I need a lot of resources, right? Even if it's computational, right? DFT time, I need to do my classical molecular dynamics, molecular simulations, right? If I need to do experiments, right? How much data then do I need to do? How many materials, how many chemistries, right? And maybe we think a lot of data in a particular system is good. It's like, yes, but maybe that's not the right type of data. We need different kinds of data to be trained to train some of these models that we're interested in. Okay, so how do we think about generating these data sets to then train some of these machine learning algorithms? It's something that we've been thinking a lot about, and something that I want to tell you about today. So first line that I will tell you about is how do we leverage existing data, right? There's already a lot of data out there, okay? What are the techniques that would allow us to leverage what's already out there and move forward? And then in the cases where we don't, how can we be efficient when it comes to our data generation? Okay. So in our case, right, we're interested in things like energy storage, gas separation, absorption. So our workhorse really is grand canonical Monte Carlo simulations. Okay, so in grand canonical Monte Carlo simulations, you fix your chemical potential, your volume, and your temperature. And so your number then in this case of your adsorbate is allowed to fluctuate. You converge your simulation, and then you rinse with, right? You have that amount adsorbed. That's great. We're looking at MOFs, right? So this is the example of MOF 5. We usually hold them fixed at the crystallographic precisions. Turns out for most cases, that's an okay assumption. There are some where it's not. We can talk about those. Very general force field parameters, in this case, universal force field. And we look at things like, say, hydrogen absorption. Okay, so to also treat it as rigid, we have a center of interaction and center of mass, and then we also have charges to get at the quadrupole interactions. And so these models have been used around for a while, right? We want to think about, well, how do we match up with experiments? Here, this is an example of an absorption isotope. This is how much is absorbed, the function of pressure. Here you have it at room temperature, okay, where the empty symbols are the simulations. And here you have it at 77 Kelvin. Now, each one of these empty symbols is a separate GCMC simulation. Right, so now you can start thinking about, okay, well, if I want to characterize the absorption isotherm of a porous material, how many simulations do I need to do for one material at one temperature? The whole range of pressures that I need to do. Okay, so we started thinking about this, and like, okay, well, we could be selective in terms of what pressures we look at. And we've done so now for hydrogen and methane. So we have volumetric adsorption versus gravimetric adsorption for both hydrogen and methane. Each one of these different symbols is a separate structure. Okay? And the different colors correspond to different crystalline topologies. Okay? And so we see there's a sharp rise in the adsorption, and then there's a plateau. This is essentially it's called the empty tank limit. So you're essentially, your material is so big, you're essentially just like an empty tank. Okay, so we have this plateau. And then we look at methane, we see very much a similar behavior, and similar topologies also occupy similar parts of that material space. It's like, okay, that's interesting. Can we leverage that in some way? Can we use as an example to maybe, right? I don't need to do, in this case, 13,000 simulations for this. Can I leverage information from one space to reduce the amount of simulations that I need to do the other one? Okay, so we know from the literature that we can start using neural networks to actually model some of these absorption processes, where now we can start looking at surface area, right, volumetric, gravimetric, void fractions, pore sizes, okay, to actually then do the training and get at some of these absorptions. So that's great. Okay, so now if I can do that with a neural network, I can now start thinking about doing something like transformers. Okay, so what is this? So we have our normal training. So I have my source task, okay, where I'm going to use all the data that I have available to me. Okay, I'm going to take that model Okay, I'm gonna hold all the weights fixed, and I'm only gonna let the last layer, the weights of the last layer change as I'm training it on a new target task. Okay, so that's what I'm gonna do. I'm gonna say, right, a different source task and target task. And then for my target task, I'm only gonna use 100 data points. Okay, so instead of using all 13,000, I'm gonna use 100 instead. Okay, so I can, right, I can bring this, the amount of data I need by orders of magnitude. Okay, so this is what this looks like. So I have hydrogen absorption as my source, methane as my target. When I do direct learning, so if I try to learn just 100 data points, right, without transfer learning, actually I get pretty good agreement for, this is all 1,000 random sort of selections of data. Okay, but when I do transfer learning, I see very good performance, right, across all the different batches. Okay, so that's great, right? So that means I can take this source task, okay, and use it now in the target spec. Great. So we saw this, we got really excited, and then we thought, okay, can we get greedy? Okay, now I use pure component absorption to say something about mixtures, right? So something much more complicated. Okay, and I see the results for direct and transfer learning, and it's horrible all around. Okay, we cannot do this. We cannot use, say, hydrogen as my target, and then say something like xenon krypton absorption. Hydrogen as my source and xenon krypton is my target, right? The performance is just not there. And then you start thinking, okay, well, why? Well, you have to look at the feature importance, right? So if we look at my source and my target, right, we see similar feature importance distributions, okay, when it comes to the actual model performance. Whereas when I look at the one that's a mixture, first of all, you could argue that I don't even have the correct even descriptors to even do that task to begin with, and we didn't do. Okay, but now we have sort of a good sort of rule of thumb of when we can use transfer learning and when we can't. Okay, if you have a source that is, say, cheap, easy to run, quick, fast, okay, and you have a good sense that those same features that govern that process will be relevant, and you do target, which may be expensive, dangerous, perhaps. Now you can get away with a lot less data in that space to train it. Okay, but right, it has to meet that condition. Your feature importance needs to have some resemblance to each other. Okay, if you don't, then you won't be able to do anything together. Okay, so other things that then we can start thinking about is, well, can we use now these techniques to actually learn something new about the material space itself? Okay, so now we're going to start looking at transfer learning across the material space, right? Our scenario was, and it's the way we were thinking about it, it's like, look, doing absorption experiments with different gases is easier than having to, say, synthesize a bunch of new materials. So can I have my source be a set of materials and have the target being a different set of materials? Can I do that across this material space? So I took my features, I do a principal component analysis. Okay, now I can do a clustering and now have different clusters. I can have a direct learning on a cluster. I want to transfer learn to a different cluster. I want to study how does transfer learning performance depend on, say, where they are in this material space. Okay, so I can look then at the final models and look in terms of distance, kind of makes, I mean, we're still getting very good performance, but we definitely see that there's a dependence on the distance. So the further you are in that PC space, the worse your performance for transfer learning is going to be. Makes sense? And then we look at sort of the performance of every cluster as a direct learning cluster. Okay, so we see that number 4 here is actually the ones that performs the best. So now that's interesting. At least for me, it's interesting. What that tells me is like there's a set of materials that are a really good foundation for information for everybody else. Right? I have a set of materials that lie in this space. Then now I can start, right, I can use it to characterize the rest of the materials, right, and have now really good transfer learning space performance across this material space. And so we can use these algorithms to actually learn something new about this. Okay, so these cases are where we have existing data. Right? We have a source, we have a target. Great. What about the cases where we need to start from scratch? Okay, so The example that I just gave you, right, is an example of supervised learning. It's what we call passive learning, where you have some training data, you train your model, you validated it, and you go ahead and you use it moving forward. Okay. Active learning, okay, it's going to come here. It's actually going to make a training data request. So the model itself is going to say, hey, excuse me, can you give me some more data in this space? Or can you give me some more data on that space? So in many ways, I'm following the algorithm's instructions. And the way we do that is going to be with a Gaussian process. Right? So with the Gaussian process, we have a mean prediction. We're also going to have a covariance matrix describing the relationship between my data. And so what that turns into is I have the mean of the prediction, but I also have predicted uncertainty. So I can use the predicted uncertainty to help me make that decision as to where I go next. Okay. If you talk to people in the process engineering community, it's called sequential design. Okay, so you're going to have some data. Okay, so in our case, again, absorption, temperature, pressure, you pre-process, you go through your training, you have some predicted uncertainties. Hey, where's the maximum error? Are you below some threshold? If not, take that point of maximum error, do the molecular simulation or do your experiment, add that data back in, and keep going iteratively until you reach some pressure. That's it. Okay, so let me show you what this looks like. So this is absorption isotherms again. So I have methane versus pressure. Here, these black points are actual, right? That's how the first couple of data points that I fed the model. The red line here is the prediction. This is the GP prediction. And the error bars are also the predicted uncertainty. Okay, so just from a first look at this, you say this, okay, this just looks nothing like an absorption isotherm. You have decreasing absorption with increasing pressure. No, right, that doesn't make any sense. Doesn't make physical sense. But the model of these is being honest about what it knows and what it doesn't, or what it thinks it knows and what it thinks it doesn't, and tells you, okay, this is my point of maximum error. It's like, okay, well, I'm going to run that simulation. I'm going to give it to you, and this is now the result. This looks like a pretty good estimate now, right? You see now the predicted uncertainties also go way down. We go one more, and now I can compare directly the GP prediction to that of the actual GCMC simulation. Okay, so I showed you before, so all the simulations that I would need to do for one isotherm. Here I just needed 5 simulations. I'm still able to now develop a surrogate model that as people will describe this. Even when I zoom into the low pressures, I get very good agreement. Okay. I can also now, right, that was just pressure, I can simultaneously do now temperature and pressure. Okay. And we see very good agreement for things like methane, CO2 across all of that space. Okay. Now we can start looking also at the errors. So this is the predicted error. This is the actual error, right? Because I think that's an important question. Can I trust the predicted uncertainty? Can I trust what the GP is telling me? Well, we see very good agreement, at least in the trends, in terms of the sort of decrease in error. You actually end up with similar percentages once you're done with the simulation. Importantly, when I look at how much it would have normally taken me, or what is sort of kind of what people do when they're kind of characterizing absorption in these spaces and temperature and pressure, take around 800 simulations, we just needed 80 to navigate temperature and pressure. All right, so I'm bringing down the number of data points needed to develop these models by an order of time. It's like, okay, so now we can think about adding composition into the active learning. And so this is really nice, because now this type of framework is actually very modular. You can start thinking about, okay, I can do temperature, I can do pressure, now I can do composition because I want to do mixtures. And I want to understand that space. You can just add them here because we have a different molecule, we need a different GP. We have one for each molecule. That's really the only kind of new thing that we bring in. We can think about how do you terminate things, and we've developed some things there. What's your termination criteria? But otherwise, everything else stays the same. Okay. And so now we can start thinking about navigating pressure and composition. So here, the state of the art for these types of things is ideal of source solution theory. So it's going to be here in red for methane, and in purple for CO2. And my GP and my GCMC, they show great agreement, but IHT is just nowhere near the molecular simulation. Okay. Right, because I'm giving the GPs the actual data from the GCMC simulation. Okay, I can also do it now doing pressure, temperature, and composition, and I require about 5 to 6% of data you normally require. Okay, and I have about in the worst case, about a 10% error, mean relative error in this piece, right? So you can tune this to whatever level of final uncertainty you feel comfortable with. It's like, okay, that's great. So we do temperature, pressure, precision. In my sort of line of work, right, when we do molecular simulations, some of the things that we think about is like, well, what can we do that maybe it's not necessarily available to experiment? Okay. So we think about what we call alchemical molecules. So what I mean by that is when we describe these interactions on the computer, we have this, in most cases, a Leonard-Jones function. Okay, which you have a sigma, you have an epsilon, which essentially describe those interactions between your molecules you have. Okay. So there's a particular set of those that we call methane, that we call nitrogen, that we call hydrogen. Okay, well then if I'm able to now put into the act of learning that sigma and epsilon space, I'm moving in this sort of fictitious chemical space. But if I'm able to describe it all in my construction, I'm also describing the real molecule. Okay, and so this has been done already. They used neural networks, and they were able to show that, yeah, when you train machine learning algorithms on this space, you can actually make very nice predictions of real molecules. So that's great. So that we're able to do that with neural networks. Can we do this with active learning? And if we're able to do it with active learning, what are the data savings, right? Because at the end of the day, that's what we're looking for in this case. Okay, so now I can navigate fugacity, and I can navigate sort of the rest of the parameters that describe my molecule. Everything else pretty much stays the same. Okay, so now I can start looking at sort of who is my worst performer, my best performer, how much data am I saving by just navigating for each one of these materials, how much data I'm saving. So if your worst performer, you want to be around 0.85, then you have about close to 85% of savings in data. Okay, great. Now let's get greedy. Now I'm going to simultaneously navigate the material space, right? So that same principal component space that we did before, fugacity, right? Which is my thermal conditions, and the alchemical space. We're able to train, again, very accurate models, okay, that are capable of describing absorption in this complete space. I just needed 6,000 data points, where the original neural network models needed 5 million. Okay. So now with these active learning techniques, again, orders of magnitude savings to generate that data space, right? Generate surrogate models capable of accurately describing that. Okay, great. When I think about more generally, really what we're doing is trying to understand phase equilibrium. Okay, when we think about phase equilibrium and mixtures in chemical engineering, we think about activity coefficients. Okay, so activity coefficients, right, at the heart of many of the things that we want: VLE, Henry's constants, LLE, solubility, solid liquid equilibrium, support. So can we now combine some of these techniques with these activity coefficients? So we're going to take NRTL as our ground truth, and we're going to model our GPs. We're going to use our GPs to model activity coefficients, and you can start seeing how it's navigating the space. Importantly, because I know thermodynamics, I can get ahead of the GP in the sense that I know, right, that pure components, my activity coefficients are 1. Okay, so I'm just going to load this up with virtual point. Okay, because right again, I know thermodynamics. I'm not going to wait for the GPU to learn it. I can pre-feed it. Okay, so great. So now I can start thinking about navigating these spaces. If I now look at what my performance is like for various mixtures, some more complex than others, some have azeotropes, some don't. In about 7 iterations, I get about 0.5% error for describing these activity coefficients. Okay, awesome. Again, the notion, though, of using my thermodynamic knowledge to my advantage comes through again. So here's what I'm going to do. I'm using a GP for my activity coefficient. Okay. I also have a predicted uncertainty for that activity coefficient. I'm going to propagate that through the phase equilibrium equation, and I'm going to use that now to guide the next point I'm going to sample to get the activity coefficient. Okay, so I'm going to use that as my acquisition function. So this is what this looks like. So in black, I have the real. I started with ideal. There were 1, 2, azeotrope, 4, and I'm done. Okay, so I just needed 4 data points along this phase equilibrium to actually get something that's really, really accurate. Okay, this is for a binary system. We also have done it now for ternary system. And we've shown this also works for molecular fluid, it works for solid liquid fluid. Right. Where again, right, you can now start describing these space equilibrium processes. Okay. So then that tells us about how to go about data. The other part is, right, how do you turn those databases, how do you use various descriptors to then as inputs to that machine learning, okay? So these descriptors are going to be very important because they're going to allow you to actually navigate this thing. And so I will show you what it is that I mean, okay? So in the state of the art, you have sort of different molecular descriptors. There's new ones coming out. Right, so you have fingerprints, you have smile strings, Coulomb matrices, electronic densities, so forth and so on. Okay, and so they contain information to different degrees, and you can turn them into machine readable things to various degrees, right? Their interpretability sometimes is a question, right? So I've been looking at smiles strings for quite some time now. I cannot picture in my mind what this molecule is without seeing it. Right. So I think there's a little bit of that loss of intuition. Same thing with, when you start fingerprinting and then you see this bunch of ones and zeros, like, I'm sorry, I do not know how to read binary. Right. So, right, I think part of it is lost. Right. And I think that's something that us as scientists that we really value, and that is our ability to interpret the things that we are using to make prediction. Okay, so in that vein, we're going to start looking at sigma profiles as one of these descriptors. Now, sigma profiles have been around for a while. Anybody who's done anything with Cosmol RS, Tulamol, things like that, are familiar with these. And so what these are unnormalized histograms, essentially of surface polarity. Okay, so you have then negative parts of your histogram, positive parts, which represent the negative and positive polarities. You have an apolar part of your graph. So that's great. And then, based on the size, you can also tell some information about the size of the molecule. You can get a sense of hydrogen bond donors, acceptors, right? So you still retain a lot of that chemical information that will help us. Okay. Great. And so they've been used. So this is in the context of something like an ionic liquid. They've been used to make predictions of various physical properties with great accuracy. So we have a sense already that, yeah, this should work as a descriptor and it works very well with machine learning algorithms. Great. So first thing we're going to try using convolutional neural network that it uses to make predictions of molecules. The reason we chose a convolutional neural network is that they work really well when you have to keep context in mind, or in other words, when you have highly correlated information. Okay, so in natural language processing, for instance, convolutional neural networks get used quite a bit. Right? If you want to understand the meaning of a word, well, it's easier to do that if you know what a sentence is from, right? What is the context that you use? Right, so convolutional neural networks are really good for that. And the way you have different filterings that help you then sort of keep that context in mind. So we're going to apply that to our sigma profiles. And we're going to use that as an input. We're going to add temperature also as an input to another module to then make predictions of physical properties. We're going to take databases that are available in the literature. So that's great. And then we go to the CRC handbook to actually get some of these specific properties that we're interested in predicting. Okay, so we show really good predictions, right? Molar mass, boiling temperatures, vapor pressures, even though we're spanning, quite a big the range of orders of magnitude. Same thing, vapor pressure and solubility. We get very good performance, right? So that's great. We're able to use that with a convolutional neural network. It's not quite what we want, though, right? We want to be able to navigate some of these complex spaces. So the state of the art when it comes to that is really variational autocomp, right? So the idea is you have your smile string, you pass that through an encoder or neural network. It collapses that to some latent space. Okay, and simultaneously you train that to be able to recover the same thing that you put in. Okay, essentially, in other words, this is just a really fancy compression algorithm. When you go and you zip something, this is very similar. I'm just zipping a smile string. Okay, now what happens? I can take now that latent space and make that an input to a new machine learning algorithm to do property prediction. Now, why would you do that? Well, optimization algorithms work really, really well in continuous spaces. You can do discrete optimization, but that's significantly hard. Okay, so now we're going to take something that's discrete, carbon, hydrogen, and oxygen. Okay, we're going to make it continuous. Now apply optimization algorithms with this new space, and now do optimization on that latent space, and then use my decoder, right? Then navigated, right? We navigated that latent space, use my decoder to get in model. Okay, so that's the idea. Now, what does it take? Now, different VAEs will have different levels of sizes. So one of them required 108,000 molecules, another required 250,000 molecules, right? So now you have issues as to sort of different sizes. What happens if you add new molecules? You have to retrain everything. These things are extremely difficult to train. And then you ended up with latent spaces of 156 dimensions and 196 dimensions. So we're losing again some of that interpretability that we were complaining about before, right? How interpretable is that latent space? All right, so question is, can we use now these sigma profiles as part of that space? When I start navigating that space in the same way that I would when these latent spaces were navigated. So first thing we did is, okay, well, we need, in order to do that, we need something that gives us uncertainties. So we're going to say, okay, can I use GPs that we did before, but now on sigma profiles? The answer is yes. Not only can we do that, but it's also significantly more efficient. It takes me about 10 seconds to train a GP, about a week to train a convolutional neural network. So we have, right, large efficiency there. Okay. And so now I'm going to see if can I do optimization in these sigma profile spaces. So this is my sigma profile space. Just for visualization, I'm going to collapse it to a PCA space, so we see how these things are working. So I'm going to ask it, okay, can you find, say, the maximum boiling point within this data? So you have about 1,500 molecules. There's no pre-training. Okay, it's like, here you go. Start and let's find it. So you can see here how the algorithm is jumping around the different kinds of molecules that it's looking at, different halogenations, alkanes, aromatic rings, so forth and so on. So this is the molecule with the largest boiling point. This is supposed to be stacked, but and we started with carbon monoxide, which was the worst, right? And so we see now how the error of my model is changing, and then in blue is actual the predicted boiling point temperature from the model. Okay, and it took about 15 iterations. In 15 iterations, with no pre-training of this model, just using sigma profiles as the input, I asked it, find me the molecule with the highest boiling point. In just 15 in a space of 1,500. Okay, so now combining these chemical descriptors with some of these active learning techniques allow us to navigate these spaces quite efficiently. So now I want to summarize, right? So we have, in our field, we have research efforts along how do we generate these databases, how do we generate then the data, how can we be efficient, how can we leverage existing data, and also developing descriptors to help us navigate these spaces. And then now combining also how we do these descriptors with generating some of that data. Okay, talked a little bit about temperature, pressure, and absorption, transfer learning, activity coefficients, and phase equilibria, and then navigating these molecular spaces. Thank you very much for your attention. I'm happy to take a question.
Awesome, thank you very much. I also shamefully failed to mention your greatest accomplishment as an academic to date when I introduced you, which is that you were given tenure last week.
That's right. Thank you.
Sorry about that.
Good review.
Any questions for Professor Colón?
Would you explain how you calculated kind of true activity coefficients in your active learning project?
So for that activity coefficient, we took them from NRTL. So there's already thermodynamic models that have these, right? Presumably though, right? If you're doing a phase equilibrium equation, you can sort of back solve for the activity coefficients. If you're doing molecular modeling, then you can apply, right, KBIs or others to get activity coefficients. So in scenarios where we don't have easily accessible data like a thermodynamic model, you can think about doing a molecular simulation to get at these estimates of the activity coefficient.
Go work.
So when you talk about the efficiency of certain materials for transferring to others, you have the cluster model extending into new materials. How do you I mean, is that confounded at all by sort of the shape of the material space that you're starting with? Like some clusters are closer to a lot of other clusters to begin with.
Right, so the question is, when you're judging the efficiency of any given cluster to be a good source, is that biased by just the way the material landscape looks like in the species space? Yeah, the answer is yes, absolutely. Right, and that's good because it matches our intuition. The true value now comes is like I can tell the experimenters like, hey, we want to understand how all these other materials have. If in your lab you have these sets of materials that we found lying in the center of the cluster, you can run experiments on that set of materials and help you make easier predictions in other spaces where you don't have it. So that's the value there. But you're absolutely correct. Yes, we're going to be biased by where we are in that space.
I'm curious about commercialization.
Mhm.
Can you name a couple of companies that commercialize MOFs?
Sure, yeah, so there are a couple. So not very far, there's Numat. So when I was at Northwestern, my colleague, Chris Wilmer, he helped start that up, and now that's now ongoing, and they've been around for a while now. So here in the US, there's others in the UK, so Immaterial, it's one that's out of the UK. And so there are other sort of more chemically focused or process focused companies that use MOFs, and so this depends on MOFs. So there's Sponte, out of Canada, and they're looking at a sort of DAC type technologies, and they're using MOFs. So there's various examples now where MOFs have been successfully commercialized.
Nice talk.
Thank you.
So back to the transfer learning
Mhm.
case, so do you think that there exists like a universal set of descriptors that one could you hypothesize that such a set could exist, that then you could sort of use it for prediction of many related materials classes?
That is my hypothesis, and something I'm trying to test.
Okay.
Especially now, right, with the 100 million materials, and there's only a bunch of these databases of chemicals themselves, right? That's where we can start to get to test, right? And so then the question, right? So now there we have data that we can use and then leverage. The question now becomes, is it what are my descriptors?
Right.
Right. So you can start thinking about, I'm just going to do them all, go and already care, get them all, and then publish them, do a feature reports analysis and figure out which ones are important. So the question is like, is there a universal set versus I'm just gonna feed it all and do whatever? I think there becomes a little bit blurry, but yeah, so I think from my experience, the more information you have in the chemical descriptors that is relevant to what you want to predict, the better you will be. So there's still that, you still have that caveat of whatever descriptors you come up with need to be relevant.
Right.
Right, there have to be some physical connection.
Right.
But yeah, so in a way, that's what we're trying to get at the signal profile. Where we're trying to say, okay, well, what other things can we predict? Well, we know we can do solubility, we can do boiling point, we can do vapor pressures, right? Can we now get a little bit more into mixtures? Can we think about maybe some harder things to think about, drug efficacy, like other things, right? So a couple of orders sort of removed from that process.
I noticed that you learned some thermodynamic parameters. I was wondering if you could use those parameters to embed it with traditional some framework like Lamiel absorption, so that your model become more interpretable.
Yes, absolutely. Right. So the question, can you take sort of what you've learned thermodynamically and now input it into other thermodynamic models to help with some of the interpretability? Absolutely, you can. Yeah, and now you can start thinking about if you have your model, right? You can think about learning the parameters themselves. You can think about doing sort of other techniques. So these are this model-based design of experiments, things that you can do with analyze future information matrix and things like that, and then combining that with some of these ML things to help you. Right. So now the question is, right, which is a very important question, especially for experiments, like which model is the one that I should be using to model my process? Right. So now you can think about designing experiments that will help you discern between models and presumably the correct physics. So yes, you can definitely do it.
To be on that there.
So underlying all of these activity coefficients, they give to an equation, which on the first for both systems are very in equilibrium. You think that maybe you can use all of this data to find a numerical closure and expand gives to a more complex system? Is that, are we,
So that the question is, can we, or do you think that we can?
like you would be giving a pickle?
Yeah, So I told you what we have done so far. We've taken this and passing them through, because all these activity coefficients are now described by a GP. Right? The kids do usually think about it in terms of the models. It's like, can I show them my model is thermodynamically consistent? Now I don't have a model, I have a GP. This is this is something else. We can still use Gibbs Duhem to now evaluate the thermodynamic consistency of these GPs. And so forth binary. We haven't looked beyond that. However, though, I would argue that you can use this framework to now evaluate the thermodynamic consistency of data. Right? We usually think about thermodynamic consistency of models. Well, now I just have a model that just fits. Right? And now and I've shown that when the data is thermodynamically consistent, I can show that I meet the closure conditions. Now I can start looking at other data points and see if that data itself, if it doesn't meet that closure consistency, I know it's not a model, it's the data it's a fault. So that's how we were thinking about it. We have not thought about it, sort of like making it more, so more even bigger multi-component systems, but thank you.
There. I just really appreciated seeing the efficiency gains you get from sort of embedding the machine learning to do the difficult activity coefficients work inside the ideal parts that we understand. And I wonder, like, if maybe there's opportunities to take that a little bit further. So, you know, in your model, in your GP, you had like the sigma and the epsilon. And then when you go with statistical mechanics to try and compute those activity coefficients, you end up doing these integrals and the cluster expansions and covarials. And the sigma and the epsilon get multiplied together. And I mean, is there a way to kind of collapse this even further, taking guidance from those tools?
So yes, and that's something that we're looking at. I think that there's questions there as to almost like a coarse grain type thing. So it's like, okay, do I use a GP for the epsilon and a GP for the sigma? Do I use a GP for the function that combines them together? Right? And so different levels of coarse grain, if you will, like, you know, from the surrogate model, what exactly does it describe, or what do I want it to describe, and how active I want it to be. So we've done now, so we've used KBIs now, so we have paper in preparation and looking at some of the G parameters and using GPs to strictly look at Gs, and it works beautifully. And then the reason it works is because it's the activity coefficients. Activity coefficients are nice and smooth and will, for the most part, very well behaved. So if you're able to say make a prediction or do a calculation of an activity coefficient in a single phase, the extrapolation is not hard and it's not bad. Because the extrapolation rate for when we're doing a phase, including phase separation, that's governed by the phase equilibrium. I just need to extrapolate to that point. So as long as I'm near that, I should be able to actually get something pretty accurate for the phase equilibrium.
Okay, post prerogative, my question. So sigma profiles, are they inevitably doomed when you go to large floppy things? I mean, if you were to condition, if you were trying to do a generation off the sigma profile to make a molecule, when you have really small things that are rigid, presumably that's like almost 1-to-1. But as you start going to bigger and more heterogeneous things, presumably its predictive capability will decay.
So I'm gonna split this up a little by bench scale. So we'll leave polymers and that type of thing so to the end. If you have, right, so and I did show some of the molecules of these very long alkane chains, and right, so you imagine different conformations. So our first hypothesis was like, okay, I want as much of the signal profile exposed as I want. That's a neat way to do, because as much as possible. Right, and the hope is that the machine learning algorithm will learn what parts of that sigma profile are going to be important to make a prediction at the end of the time. That worked for these things. In the literature, though, you see various examples where that confirmation is very important, especially once you start looking at phase equilibrium and things like that. That makes sense, right? What solvent you're in is going to affect your conformation and therefore what signal profile you have. So there yes, you do need to take confirmation into account. We're trying to test the limits of that. In terms of, okay, at least for pure components, what can I get away with? Let's just stretch this out. Let's just be consistent. Right, because that now becomes a big question when you're trying to generate databases of these things. You need to be consistent in the way that you generate these schema profiles. So you need some type of rubric that you need to pass your model generation through to ensure that the way that you're generating your descriptors is consistent. Right? So then that's in conflict with, well, what if my descriptor isn't the right confirmation that I need? And then, well, how do I know what confirmation? I need to couple this with MD or some generative AI that lets me sort of explore that confirmation space. So that's done, that's sort of relatively small. For polymers, where now you start, so other things come into play, there are some works out there to try to generate some of these sigma profiles. And essentially you can think about sort of monomeric species, and then also sort of some of these general sort of confirmations that try to build that. But I'm not too familiar with that work, but anyways.
All right, well, thank you for an awesome talk.